Good morning. So this is the second part of our system classification. In the previous class, we have discussed about three properties of the system and classified them. Now we are going to discuss another three properties. They are invertibility, time invariance, and linearity. Okay, so this is what we are going to do in this class. Invertibility. What is invertibility? A system is said to be invertible if the input of the system can be recovered from the output. Okay, so if the input of the system can be recovered from the output, so actually output is dependent on the input. Okay, so by processing the input, you are getting the output. Now I want to get back the input by doing reverse operations. Okay, inverse operations. So then it must be possible. Sometimes it is possible, sometimes it is not possible. Always it is not possible. Okay, if it is possible to recover input from the output back, then that system is called invertible system. Okay, so this kind of requirements you generally come across the initial applications. Okay, afterwards so many signal processing applications have come up, but the basic application initially developed these kind of things in the communications, that is communication channels. So in communication channel, what happens is you have the communication, you have the especially wireless channel like free space. So a lot of disturbances are there, and the free space also acts as a filter. So it attenuates if some rain is there. So there will be attenuation due to rain. If clouds are there, clouds also absorb some energy. So they also change the characteristics of the signal in frequency domain. Okay. So basically the amplitude and frequencies and delay properties of the signal, they are manipulated by the communication channel. Okay. So now I want to get back the original signal. So what I have to do at the receiver, I have to do reverse operations for this. Reverse operations means whatever distortions happened in communication channel, let it happen. And if I can estimate those distortions, I can build an inverse filter, saying that reciprocal filter, which cancels these things. You can retrieve the input back. That means at the receiver, you can get back the whatever you have transmitted at the transmitting end, you can get back the same thing. If it may not be exactly, but it is very close to the transmitted signal, you can get out of the receiver. Okay, so that is called, that means you have to have additional circuit in the channel. Okay, that is one requirement where you get this kind of invertibility. And let us take H inverse. H inverse means I can also write H of H to the power of minus 1, Y of t. Okay, I am taking output. I want to find the inverse operation on this output. Okay, this is what I want to do. Let us see what happens. So H inverse, substitute in place of Y. There is nothing but system operated on X is nothing but Y. And when I take together, this is H inverse into H. That means H into 1 by H. H will get cancelled. So what you have, whatever you have done, you have rewinded the operations. You have done the reverse operations, means you have cancelled all the operations which you have done. So then you have an identity here, because we are representing in terms of matrices. I say that is identity matrix. Identity of input means what? I will get the same input I will get. That means if I can build an inverse filter exactly same as the system, so I can get back the input again. Okay, that is the lesson. And what is that inverse filter? That inverse filter or inverse system, I call it as an equalizer. What it is doing? Let us say, I mean in the next slide I will explain that. So by designing the equalizer to be the inverse of the channel is H. H inverse is equalizer. So H and H inverse, I have ultimately will get the transmitted thing. The transmitted signal is restored to its form. Okay. So let us see in terms of block diagram. This is the system channel, means actual system. Now at the receiver, this is the receiver. Inside the receiver, actually This is nothing but transmitted signal. This is nothing but transmitted signal. This is channel. Then this is receiver. Here you will get the same x of t is there, x of t. Same input signal I am getting by applying inverse filter here. Okay. Then this is called equalizer. Let us say, in terms of frequency characteristics, let us try to understand. Let us say channel is something like this. Okay. Channel is something like this. What it means is, you have transmitted equal energy for all frequencies. This is the frequency. This is, let us say, frequency response of the system. Frequency response of the system. H of f. And this is frequency response of the system. This is the all, what is this? This one I can consider it as capital X of f. Means, I am transmitting signal which contains all frequencies equally. What will happen at the output of the channel? That is, at the input of the receiver. At the input of the receiver, what happens? So this is the shape of the this is the shape of the output. Okay. That means this system has attenuated some frequencies here. Some frequencies are attenuated here. Here also some frequencies are attenuated. Much, relatively. Okay. So now what I have to do? At this point, I should have an inverse filter. What is inverse filter? These frequencies to be boosted. These frequencies. Okay, I will write it here. So this is F. So what I will do? These frequencies I will reduce. These frequencies are boosted. These frequencies are already boosted. So I need not boost it. So this I will boost more. Okay. I will boost these things more, something like this. Okay. So here attenuated frequencies are boosted. Here boosted frequencies are attenuated. Again these attenuated frequencies are boosted. Okay. So because they are more attenuated, I am giving more gain. So ultimately at the end of this, what I will get? Again I will get the flat one. That means attenuated frequencies are enhanced. Enhanced frequencies are a little bit reduced. Okay. So that all frequencies are equal. Because that is the characteristics of the input signal. So here also you will get the almost same characteristics. So it is called equalizer. That means you are equalizing the response of the channel. You are equalizing means you are making the response output of the output equal. Okay. That means you are nullifying the effect of the channel. Now, take one system. It is a system. What is this system? It is a squaring system, non-linear system basically. Okay, linearity, it won't support the principle of superposition. So I can say it is, in general also, it is not a straight line. It is a quadratic curve. Okay. So how it looks? If x of t is on the input, after squaring this, I will get y of t like this. Okay, positive side. So negative side, negative values also if I square, minus x of t also if I square, I will get this kind of thing. Okay, so this side minus, this side plus. So both are, after squaring, both will become positive here. Okay, so this minus x and this side plus x of same value, they are equal. Okay, so for example, if I take minus 2 and plus 2, square minus 2, I will get 4. Square plus 2, I will get 4. So these two input values, plus and minus, both have given the same output value. Now I want to get back this value. What I have to do, I have to take square root of that one. Square root of 4. If I take square root of 4, what is that I will get? The answer, you should not say plus 2. It may be plus 2 or it may be minus 2, both. There is an ambiguity. So sign information is lost. So hence, by taking just a square root of the output, see why I am taking square root of the output? Inverse system means x of t square root of y of t. This is nothing but your h inverse. If this is h inverse is x of t equal to square root of y of t. So this inverse operation is not able to give the input back. There is an ambiguity here of sign. So naturally, this system is not invertible. It is not useful system. You cannot get back exactly same input from the output. Okay. So that is what. Now, fifth property is time invariance. A system is said to be time invariant if a time delay or time advancement leads to identical time shifts in the output also. That means when the input is, see, you have a input, you give the input to a system, you have one output. Okay. Input and output. Now, delay the input by some units, output is also delayed by 1 unit. That means input output system is there in between, input output. If X is delayed, Y is also delayed by the same amount. Okay. So that is what, that means system is insensitive to the time delays, time shifts. It may be delay or it may be advancement. Both are called time shifts. So a time invariant system do not change with the time. That means the characteristics of a system should not change with the time. So then in that case, you have to call it as time invariant system. Otherwise, if the system characteristics change with the time dynamically, you can say that it is the time variant systems. Okay. But several times in real life, most of the times, probably at minute level, if you see exactly, if you analyze, many systems are non-linear. I mean, time variant systems. Their characteristics will change with the time slightly, but the change is very small. So you can say that it is time invariant for a shorter period of time. If I take shorter period of time, you can say that the system is constant. Its characteristics are not changing with time. Time invariant system I can assume for shorter periods. Take 1 millisecond, 100 milliseconds duration. The system characteristics won't change. And take another 100 milliseconds. Within 100 milliseconds, the system characteristics won't change. Okay. Like that, for shorter durations, time variant systems can also be approximated by the time invariant systems. What is the condition for time invariance? First of all, if I want to get a time invariant system, what kind of systems appear as time invariant systems? What are the conditions required for a system to be time invariant? Consider an input x1 which gives output y1 when operated by a system H. Okay. H is a system operating on x1 giving the output y of n. Okay. Now let us say that x1 is shifted by t0 seconds. It is delayed by t0 seconds. Then what is this? Let us say the output of this delayed signal is y2 of t. What is here? H of x1 of t minus t. Because I have delayed the input, I have to call it as t minus t0. And it is operated by the system. Now what this shifting operation, I can represent as a shift operation s to the power of t0. Okay. So there, previously when we studied sk I used, this is the discrete time shift operator. What about this s to the power of t0? It is a continuous time. This is discrete time shift operator. Continuous time operator is s to the power of t0. Any shift is possible here. Okay. It is not only one sample shift. So this continuous shift system is expressed by s to the power of t0 of given input. Okay. Now considering these two operations. What are these two operations? One is set of operations imposed by the system on the input. Then because of the shifting of the signal by itself, signal input itself is shifting. That shifting operation. So one is system operations, other one is shift operation. If these two, first system operation, then shift operation on the input, then you are getting y2 of t. Call this as equation 1. Let us go to the second one. Now what I am doing, I have not shifted the input at all. I am just taken the output and shifted the output. Take output y of t, shift by t0 seconds. It is represented by s to the power of t0 y1 of t. unshifted version, original output. Original output is shifted by T naught. So the shift operation s to the power of T naught comes into picture here. Now replace this y with h of x of 1 because y1 is obtained by system operating on the x1. So h of x of 1 substitute, then take these operations on the original signal. Okay. So what is this one? Shift operation followed by system operation. What was earlier one? System operation followed by shift operation. Here, shift operation followed by h. If these two are equal, that means equation 1, equate the equation 1 and 2. If I equate these two equations 2, okay, because this is the thing which I got by delaying the output. Here, delay the input and apply to the system, you will get the some output. Okay, that output after applying the delayed input is on the left hand side. Input is not shifted here, output is shifted. Directly output is shifted. In the first case, only input is shifted. Okay, in the second case, only output is shifted. These two are same. I want to prove that these two be same. In that case, this operation should be equal to these operations. Means the order is not significant here. The operations can be done in any order. If a system satisfies this condition, that is the order of the system, order of the operations on the thing is not, this combination both are same, then you can say that the system will act as a time invariant system. So what is this operation? It is called commutation. Commutative property. Okay, we use in set theory or algebra. We have the distributive property, commutative property. Okay, like that you have. Okay, associative property like that. So here it is commutative property. That means order is not important here. If the system satisfies this condition, then that system becomes time invariant system. Otherwise, it cannot act as a time invariant system. Okay, so take the one example of inductance again and take one inductance here and prove that the inductance is an example of a time invariant system. Inductance is a time invariant system. This is what we have to prove. Okay, so same thing, Vt across the inductor, Vt. What is Vt? Voltage across the inductor, and current apply over the voltage. So output is the current here. Input is the voltage, output is the current. Okay, so here actually I can write it as I here, and I can write it as I can write it as V here, I can write it as I here. Okay, now they are related in this way. Or when if you want to find, let us say other way is, you have the output here across the inductance. So input is I. Okay, I applied the voltage here. Okay, I applied the voltage as input, I am getting the output current. Okay, take this one. So in this, let us try to prove that what kind of system it is. Response output of the inductor for a shifted input. First shift the input. When you shift the input, x1 t minus t naught. Substitute in the equation. You will get here tau minus t naught. Okay, and here it is t. See here, minus infinity to t. It is a memory system. And by change of variable, tau prime equal to tau minus t naught. This tau minus t naught you replace with tau prime. Okay, tau prime. And this t automatically will become t minus t naught. Okay, tau means tau minus t naught. T here, t minus t naught you will get as the limit. Okay, and what about this dt? dt will become dt prime, because here this is d tau equal to d tau prime equal to d tau. This is constant. Okay, this is constant anyway. So you have replaced this, call this as equation 1. So what you have done, shifted the input for the output. Now what I have to do, Don't shift the input. Give the input as it is. Delay the output. So that is what is this is t minus t naught. If I do same equation, whatever I have earlier, if I substitute there, what is that one? So here t is replaced with t minus t naught. Okay. Here t is replaced with t minus t naught. How? In the previous one. This is what? Here there is a t here. So t I am just replacing here. This is t. This is t. So this t and this t both I am replacing with t minus t naught. So t minus t naught here, t minus t naught here. I am just replacing with that one. Okay. Now, so what is the original response of the inductor shifted by t naught seconds? I mean same thing here. So whatever, I mean I have repeated here. This 2 is shown here. I have repeated here. The equation 2 again I am repeating just for comparison purpose. So these two now, if I take these two, I mean, okay, 1 is this, 2 is this. See, these two are, because this is tau prime, only change of tau prime. It is a dummy variable. Tau or tau prime, it doesn't matter, because variable of integration of variable is always a variable of integration is always a dummy variable. So these two equations are equal. That means 1 equal to 2. So I can say that it is a time invariant system. Okay. So this is just I am skipping, this is not required. Next, linearity. A system is said to be linear if it satisfies the principle of superposition. What is principle of superposition? The response of the linear system. The response of the linear system to a weighted sum of input signals is equal to the same weighted sum of output signals. Okay. So I have taken 10 inputs. I have added them and I am giving to the input. What about outputs? So each input, 10 inputs will give individual outputs there. I add all outputs are added there because I am assuming that is a linear system. Okay, let us say they are added somehow. And so if these are weight sum means what? Not adding, and is scaling and adding. Okay, weight summation means just adding. Multiply each input, 10 inputs are there. Multiply with A1, A2, A3, and A10 like that. Okay, scale each input and add. That is called weight sum. Then whatever weights I have given here, same weights are applicable at the output. Okay, in the output also, the outputs are weighed by same thing. Okay, it is the sum of same weightage. Okay, I will explain with example. So this is what I have taken x of t input, which is sum of n inputs. N inputs, that is x1, x2, x set of inputs are there. Then I am multiplying each input by a weighing factor a1, a2, an, and this is applied to a continuous time system. Okay. Now, what is the output? Y of t equal to h of x of t, and substitute in place of x, substitute this from equation 1. Now, if the system is linear, we may express, if the system is linear, this is what? Same weight sum. Whatever weight sum I have given, whatever weights I have given for inputs, same weights I am using for the output summation also. If it is linear, because I don't know whether it is linear or not. Okay. Assuming that if it is linear, the outputs will look like this. And what is this? What is the y1? y1, y2, y3. y1 means h of x of 1. y2 means h of x of 2. So individual outputs are operated by the system to give individual inputs are operated to give individual outputs. So if individuals are weighted by some factors, output is also weighed by same factors. That is what is called linearity. Okay. Now, this is individual. So substitute this here. This is y of t, correct? This is y of t. Substitute for y of t. Y of t, yi of t is nothing but h of xi of t. Okay, this scaling factor will be there. So this is the thing in a way. Now what is this? Equation 2 and equation 3. Both are y's here, y. Equate them. Then what is that? If the weight factors are commutable with h, that means weighing factors multiplication by a1 and H, if they are commutable, that means you may first multiply and apply the system operation, or first apply the system operation, then apply the weights. Both won't matter. Okay. So if the weights and system operation can be commutable, then the system can be called as linear. Okay. Order is not important. AI and H, first H and afterwards AI, or AI or H. Both can be multiplication and system operations. They both can be in any order. Then the system becomes linear. Okay. Basically in all these properties, mostly because time shift is there and scaling factors are there, because that is independent operation, independent variable operation. This is a dependent variable operation. So whatever the operation is there, if there is a commutability of operations which you are doing on inputs or outputs, and which the system is doing, if both are commutable, then most you can become a linear. Okay. So like that, you have the I think I have completed this properties of systems or classification of systems. If this condition is not satisfied, that means if the system is not linear, then what happens? It becomes a non-linear system, like y equal to x square. It is a non-linear system. Thank you. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.